to have all of you with me until now for the last presentation in this conference. Or maybe you guys just waiting for the reward section at the end of the conference. Okay, my name is Zhenshuan Fan. Today I'm going to talk about three pilot scale cases about MCDI underwater reclamation in semiconductor industrial. I postdoc working under Professor Hou, and I also serve as a member at the Water Innovation Research Center. And this center also called the Winner Center. So when I discuss some question or problem with the local company in Taiwan, I always told to the company that if you join us, you will be the winner. Yeah. So we focus on the we focus on the problem-oriented thinking, and we trying to understand the problem and the wastewater treatment issues and challenges from the local companies in Taiwan. Then we can provide integrated solutions to them. As I have following Professor Hou's dedication to the promotion and the development of the CDI technologies. So I will focus on the NCDI technologies today. I also know much about the NCDI. And due to its superior characteristics, the NCDI have a lower core-ion effector, low energy consumption, and a higher salt absorption capacity and the charge efficiency. And the most important for me is NCDI have a higher water recovery than CDI. So I think most of the CDI manufacturer worldwide focus on commercialized NCDI device and the controlling system. For our laboratory, we gradually progress from the fundamental to the practical engineering and implementation. We started from a very tiny electrode to scale up the electrode surface to an electrode that bigger than my face. Okay, and we developed a small cell to the stack, and we develop the tabletop testing systems, on-site system, integrate pilot scale plant. We also publish some patent documents in Taiwan. To summarize the most important aspect over these years, I think the most important with the competition with the mature technologies such as ED and RO, I think the most important task for us is to find out a suitable target and a niche practical application target for the NCDI. Besides the technical feasibilities, we have to make sure the entire wastewater treatment process we provide to the company have the economically viable for the technologies to transition from the laboratory to the practical applications. So for the past, we talk about the seawater and the black sheet water desalination and the water soften. Maybe we can reach enrichment and the carbon capture, even liquid mining in the near future. Today I'm going to talk about is the reclamation, circular water treatment, and the wastewater treatment by using NCDI. So I will talk about the reclaimed water from the domestic wastewater treatment plant and or from the RO reject. We also do water quality control of the circulating water in a square bin tower. So the first case is involved the establishment of an advanced NCDI pilot plant. We reclaim we reclaim the effluent from the wastewater treatment plant, and we utilize sand filtration and the ultrafiltration to remove most of the suspended solid. And then we utilize MCDI system to remove the charging ions. The total capacity of the MCDI system is around 20 cubic meter per day. And it's not that we use a constant voltage of 2 volts to power the MCDI device. As you can see, the conductivity of NCDI outlets decrease gradually during the charging stage. And to achieve a higher water recovery, they are higher than 75%. Pump off regeneration process is applied as operation process. And the last, the conductivity of the NCDI outlet increased quickly during the discharge process. So it's a normal charging and discharging cycle for NCDI. And we can set the time for each stage by using this control interface in the controlling system. And the results show that the NCDI system have a long-term stability among 8 months continuously operation. We have an average removal efficiency of 75%, and the energy consumption of the NCDI module is around 0.2 to 0.4 kilowatt per cubic meter. Importantly, the energy consumption is only the NCDI module. If we take into account the system, whole system, we can find out the entire NCDI system, including the pump and the NCDI module. The energy consumption is around 1.7 kilowatt per centimeter. So the major energy consumption comes from the pump in our case. I think it's resulted from a high water pressure drop inside the NCDI module. So it seems that we still have many room for improvement in the NCDI structure design. However, we also compare the energy consumption with the same capacity of the RO system of 20 cubic meter per day. We found out the energy consumption of the entire NCDI system still lower than the RO system. And we can, as we can see, we can find out the removal efficiency decrease from the 90% to the about 65%. I think it's a result from some scaling problem happens on the electrode surface. So we increase the cleaning frequency of the electrode surface using the citric acid. Then we can notice the removal efficiency increase back to the 85%. So it's work. And according to the water quality analysis, we can find out the removal efficiency of the charged ions like total hardness, ammonium, and the total phosphate have a good removal efficiency. But the uncharged species like the COD or the TOC, there is no significant removal efficiency can be observed from our results. So looks like we need a post-treatment unit for meet the specific water quality standards. And the second case is talking about we reclaim water from our reject. The our reject comes from a purification process that's using the tap water as the inlet. And the produced water from the NCDI, we pump the purified water back to the buffer tank in front of our system to increase the water recovery. And as we can see, in the conductivity of ROR is about 1,000 microsiemens per centimeter. And the produced water from MCDI is about 200 microsiemens per centimeter. So the removal efficiency is about 80%. So by using the MCDI system in the purification system, we can increase the water recovery from 50% to 77%, and water saving ratio around 75% in this case. And for this case, this company, we provided 2 systems to them, and another system, the produced water from MCDI was as inlet for the cooling tower, another application for the produced water from MCDI. Okay. It's the on-site photos. We can adjust the number of the MCDI modules to obtain different capacity. 2 pieces for 4 CND and 3 pieces for 6 CND. And also in this case, we also operated the modules at a constant voltage at 2 volts. And the last case is talking about the water quality control of circulating water in the scrubber. The scrubber is primarily used in industry and convert the pollutant from air pollutant to the liquid pollutant. So as more and more contaminant adsorbed from the air to the liquid, the conductivity of the circulating water will increase gradually. And to prevent the conductivity of the circulating liquids is becoming too high, and that may result the poor mass transfer from the air to the liquid. Continuous water sublimation and the reject of and the discharge of high concentration wastewater are required. So I thinking about maybe I can use the MCDI system to produce a high concentration and low value brine and reject from the whole scrubber system. And MCDI can produce a purified water back to the scrubber and dilute the circular water. So I can stabilize the water quality of the scrubbing liquid at a low conductivity. Then the case I'm going to talk about is the system have 2 scrubber. And the first scrubber is connected with the electro-oxidative system for the removal of ammonia. Actually, it's transformed ammonia to the nitrogen by electrochemical technologies, but I'm not going to the detail of this part. And we can see the second scrubber here. The second scrubber connect with the MCDI system. So the purified water can go back to the scrubber, and high concentrate brine can reject from the entire scrubber system. Now, as we can see, yes, it works because a brine with a higher concentration can be produced from the MCDI higher than the original conductivity of the circulating liquid. So I produce a brine with a high concentration. So the conductivity of the circulating liquid decrease gradually and to a stable water quality in the whole circulating system. But we also found a problem is that when the conductivity of the circulating water decreased to a level, the concentration efficiency made by MCDI is reduced when the conductivity of the circulating water is low. So I modify the controlling system of the CDI. Turn to MCDI system only automatically activates when the conductivity reach 2,000 microsiemens per centimeter, and automatically stop when the conductivity decreases to 1,500 microsiemens per centimeter. As the data, you can see because the pollutant from the air to the liquid, then the conductivity increase gradually. When it's reached to 2,000, then the MCDI system has been activated. So the conductivity of the circulating liquid decrease again and stop at 1,500 microsiemens per centimeter. So I can use this system to control the conductivity in the range of what we set on the system. Yeah. So, and I want to thank the Wenjing Huang, who is a general manager, and Zhongyi Chai is an engineer, and Yanting Ke is another engineer to help me, help our team to establish the system. Actually, at that time, it's the photos about we did the installation and the hand-in process. At that time, I am unsure about the MCDI performance, how's going about the MCDI performance, but I am sure that it's the highest MCDI system ever in Taiwan. It's very high. Okay, so let's go into the conclusions. So as I mentioned before, we discussed the technical feasibility in the laboratory. It's talking about the removal efficiency and the water recovery. But the challenge we face is about economic feasibility. For the second case and the last case, I didn't mention many indicators about the economic feasibility because we're still working on it. I hope I have the chance to share the data in the near future to all of you. Thank you.
Passionate comment?
Well, first of all, it's very interesting to see that you not only have 101 the tower, but also the 101 CDI system. But yeah, I'm very pleased to see that you do this pilot work because as also David Wade was saying the other day, we need more of these pilot studies. And so it's very nice that you actually do this.
Thank you.
I do have two questions. And the first one is on the housing. You have chosen for the rectangular housing with iron plates or steel plates. That makes it very expensive. You must have ideas to actually move to other housing. And the second question, let me ask it immediately. Almost everyone who does pilot studies would actually do that at constant current. You've chosen for constant voltage, and that may be the reason why you find this decay in performance because of scaling. So what was the rationale for going for constant voltage?
The first question is about the housing, right? Yes. Because we do it in the laboratory. So so far we want to do the housing, the design of the housing, but we have not yet finished it. Okay. And for the second question, it's about I using the constant voltage because I think if I use the constant voltage, we have a much higher driving force from the beginning. So I can I have a much higher high mean absorption rate for the entire charging stage. If I using a constant current, the voltage increase gradually, right? So I think it's cost more time to achieve the purpose of desalination.
But then you have a high risk of scaling, but then you accept that.
Excuse me. Yeah.
But then because of the constant voltage, you have a higher risk of scaling, but then you accept that and you clean that with a citric acid.
Yeah. So the charging and the discharging cycle, we do it quickly. The time is much. I think the time is much shorter. Yeah. Thank you.
Other questions? And I gather you also stop the flow during discharge in order to maintain high water recovery. Is that correct?
Yes.
Okay, thank you.
Okay. Next question.
Please check that. Is online chat?